So we're going to talk about hyperbolic functions, and this is our first part. We'll talk a little bit more tomorrow as well. And like I mentioned, the hyperbolic functions, what they are is it's a special class of exponential functions. They come up a lot, like I said, in engineering. They describe waves in elastic solids. I'll just give you a few examples. They describe the shape of a hanging cable. A hanging cable is approximately parabolic, but not exactly. They describe the temperature distributions in metal cooling fins, and those are just some of the examples of how you would use hyperbolic functions. They're related to hyperbolus. I'll talk about how they're related to hyperbolus at the end, because we talk about hyperbolic and we don't really see the hyperbolus in what we do. And they're very similar to trig functions. So you'll also see them described as the hyperbolic trig functions. So let me give you some definitions of what they are. The reason that we define them this way is because they come up so frequently that we wanted to give them, mathematicians, scientists, engineers gave them their own names just to make them easier to work with. They come up so frequently we name them separately. That's kind of what we do in math a lot. So we're going to define our hyperbolic functions. And like I said, we're not going to go into a lot of detail. I just want you to have had an introduction to these. So we write our hyperbolic functions with an h at the end of our trig functions. And I call them the hyperbolic sine, hyperbolic cosine. The sine, another way that you'll hear it referred to as cinch. This is pronounced cinch. Hyperbolic cosine, or cosh. And it's very easy to lose track of signs with these because they're very similar, other than a sign change. What I normally do with quizzes and tests is I allow you a 3x5 note card. So I would say, no, do not memorize these. If you happen to, just because you're working with them, it can help you out, but I wouldn't spend a lot of time trying to memorize them. Tanh is just like we'd expect. Hyperbolic sine over hyperbolic cosine. I'm not sure how to pronounce this one. Cosine. So we start with these two definitions, and then the co-functions kind of follow from our normal definitions of trig functions. This is the Cinch. And the cotanh. Oops, I forgot my x's. I forgot my h. And that's just 1 over the hyperbolic tangent. And this is for x not equal to 0. And the graphs of these 6 functions are on page 389 of your textbook. I'm not going to draw up all the graphs, but if you look at page 389, they give you the graphs of all of these, so you have an idea of what the graphs look like. And we can define, or we can find identities based on our hyperbolic trig functions, a lot like we do with regular trig functions, with the circular trig functions. Basically, we start with the definitions. If there's ever a question about how something works with the hyperbolic functions, you can always go back to these definitions and work with them. Once we start doing derivatives and integrals, you go back to the definitions if you get confused. Sometimes that can be helpful. So let's look at one hyperbolic trig identity. So the first one we're going to look at is the squared x minus Cinch squared x. And I'm just going to start with the definitions. So this is going to be e to the x plus e to the minus x over 2 squared. And I subtract my definition of the hyperbolic sine, e to the x squared minus e to the minus x over 2. And this is squared. When I multiply this out and simplify, what do you think we get? 1. Our identities are very similar, often up to a sign change. So we have a negative sign here rather than a positive sign. So that's one place where the hyperbolic functions can be, they can be tricky because they look, some of the identities, some of the ways that we work with them are so similar to the circular trig functions that it's easy to confuse the two. So if you're looking at something that is similar to a trig function, if you end up with, when we start talking about inverse functions, we'll work with it more. But if it looks like a trig substitution, but the sign is not quite right, you might be working with hyperbolic trig functions. We can start with the definitions, and we can go through derivations for other trig functions. So a couple of others, I'm going to write them out. We won't go through them. Hyperbolic tangent squared plus hyperbolic secant squared x equals 1. Hyperbolic sine of 2x is 2. Hyperbolic sine x, hyperbolic cosine x. And the book lists a bunch of other identities on page 390. Again, don't memorize all these identities. I would recommend for a quiz or a test writing a few of the main identities on your note sheet. So this is our definition. This is working from the definition. We can get some identities. We also work from the definition to find the derivatives of the hyperbolic functions. So we just start with these definitions of hyperbolic cosine, hyperbolic sine, and differentiate the definition functions to figure out what our derivatives are. So let's look at a couple of those. Yes. The identities are on page 390. Oh, and if you guys hadn't found them already, in the very front of your book, there are pages of derivatives and integrals. I think it's like the first page, and the second page is a truckload of trig identities that you'll end up using over the course of the semester. So that's a good page to remember to refer to. All right, so our derivatives. And again, like I said, what I want to do is just kind of introduce you. I want you to have seen these. We're not going to go into a lot of depth with these functions. I just want you to be aware of them, to have seen them, and to understand a little bit about how they work. So we start with the derivatives. We start with the definitions and just differentiate. And some interesting things come out. So if we take the derivative of the hyperbolic sine, Cinch, what we're doing is taking the derivative of e to the x minus e to the minus x over 2. When we differentiate that, we end up with e to the x plus e to the minus x over 2, which is hyperbolic cosine. So to find our derivatives, we're just starting with our definitions. The derivative of the cosine, hyperbolic cosine, so we're going to differentiate e to the x plus e to the minus x over 2. And this is, all we do is change the sign here. So we get e to the x minus e to the minus x over 2, which is our hyperbolic sine. So very similar, other than a sign change. No. So I was just doing that to show how we get the derivatives. Well, once you know the derivative of hyperbolic sine is hyperbolic cosine, then you're done. So you don't have to go through this process. I was just showing you how we figure that out. And just I'll do one more really quickly. And this one's a little easier to do, not from the definition. The derivative of the hyperbolic tangent is derivative of hyperbolic sine over hyperbolic cosine. And I would just work straight with what we know about the derivatives of these using the quotient rule. And when we go through that process, we end up with over hyperbolic cosine squared, which is hyperbolic secant squared. With the tangent, it's a little more difficult to do the derivative from the definitions. But once we know these, then it's relatively easy to go through the process. And we can go through a similar process and find the rest of the derivatives. And once we have the derivatives, then we know we can figure out the integrals as well. So we have derivative of sine, derivative of cosine, derivative of tangent. I'll write out our others, and then we'll talk about write out our integral formulas. And basically, that's all I wanted to do today was show you what they are, show you where they came from, show how you get derivatives and integrals, and then you guys will be able to work with them a little bit. So our derivative of the hyperbolic cotangent is minus hyperbolic cosecant of x derivative of the secant hyperbolic secant, hyperbolic tangent. So these look almost exactly like our regular trig functions, just some of the signs are a little different. So those are the three derivatives. And then our integrals are just working backwards from our derivatives. So our integral formulas are just working backwards from our derivatives. So that I'll just write a couple, and then you guys can see the pattern. The integral of hyperbolic cosine is hyperbolic sine of x plus a constant. And we're just using our derivative formulas and going the other way. This is the hyperbolic cosine. And we can keep going from our derivatives to get our integrals. So again, very similar to the regular circular trig function. Questions? Again, all I wanted to do was define them, show you a little work with them, and then in the homework you're just going to manipulate them a little bit, work with some identities, do some derivatives, do some integration. Tomorrow we'll talk about the inverse hyperbolic trig function, and that's when it gets a little trickier. Now, in your book, they give you some in the margins. They talk about some different readings. In the book, on page 388, there's an article that they refer to that gives you a lot of really great information on the hyperbolic functions. If you guys want to read a little bit more about them. And on block day, we're going to talk about the inverse hyperbolic trig functions, page 392 to 395. If you guys wanted to look ahead a little bit. But what I wanted to do, something that they don't really talk about in the book, is having defined these. We call them hyperbolic trig functions. We say where they come from, what they are. My question was always, where's the hyperbola? We call them the hyperbolic functions. Where's the hyperbola? They must have something to do with the hyperbola. So I wanted to talk a little bit about where the hyperbola comes from in the hyperbolic trig functions. So relate them a little more closely to the circular trig functions. So that was always my question. You do not need to know this. This is just some kind of for your edification. I never, when I was in school, I never learned this. Nobody ever taught. We talked about hyperbolic functions all the time. Nobody ever told me where the hyperbola was. So I want to tell you so you guys know. So, with regular trig functions, we're rotating an angle, and we're rotating around the unit circle. So our regular trig functions are circular trig functions. They're based on a circle. And when we work with circular trig functions, with our normal trig functions, our basic identity is cosine squared t plus sine squared t equals 1. Well, that's the equation of a circle. That tells us that we're on the unit circle. So the point cosine t sine t is on the unit circle. We came up with an identity for hyperbolic sine and hyperbolic cosine. We said that the hyperbolic cosine minus the hyperbolic sine squared, we said that was equal to 1. So if we look at the point from this identity, the point we look at this point, this identity tells us that this point is on the unit hyperbola. So on the unit hyperbola, x squared minus y squared equals 1. And I'll write here x squared plus y squared. So this identity tells us that this point, hyperbolic cosine t, hyperbolic sine t, is on the unit hyperbola x squared minus y squared equals 1. So if we draw in a quick sketch here of the unit circle, and then I'll draw a similar sketch of the unit hyperbola. So here's my, I want a circle here. Where's my shapes? So here's my unit circle. Now the circle looks good. I never get my axes right in the center. So just have to bear with me on that one. So we're imagining that this point here is the center of the circle. And so with circular trig functions, we're talking about a point up here on the circle, cosine t, sine t. And here's our angle t. For hyperbolic functions, we have our axes and we have the unit hyperbola. So here are my axes, and my unit hyperbola goes through the point 1, 1, and I'm going to draw it. It's not going to be beautiful and perfect, but we'll get the idea. So there's my unit hyperbola. And that's x squared minus y squared equals 1. And this is the point 1, 0. Unit hyperbola goes through 1, 0. And so my hyperbolic angle, if you want to think of a hyperbolic angle, is we're going to a point here on the unit hyperbola. I'll draw these in red so we can see them here. So there's my point on the unit hyperbola. And this is my point up here, hyperbolic cosine t, hyperbolic sine t. Forgot my h, there we go. And for the unit hyperbola, I'm going to extend this down because we're talking about, and this is supposed to be symmetrical. And this angle here from the axis to my segment here is t over 2. So the whole big angle between these two red lines is t. Let me write that t there. So this whole angle is our hyperbolic angle t. So that's where the hyperbola comes from with the hyperbolic functions. As we're looking at a point on the unit hyperbola, we can think of this angle as our hyperbolic angle. And the area of, if we remember back to how we find areas of sectors, the area of this little sector is t over 2 on the unit circle, and the area of this sector above the x-axis is also t over 2. So that's another way that those two are, the hyperbolic functions and the regular trig functions are related. So that's where the hyperbola comes from in the hyperbolic trig functions. Is we can think of it as being a point, think of the points that we're looking at as points moving along the unit hyperbola. Okay? Yes? Negative Cinch, yes. So that should be the segment that connects these 2 points should be a vertical segment, even though I didn't draw it that way. Okay? Questions? All right. Homework. So we're on page 396. There you go.